Hello, my name is Kyuho Be. I present our paper 5D light field synthesis from a monocular video. This work has collaborated with Andre Iban, Hajime Nagahara, and Inkyu Park. Commercially available light field cameras have difficulty in capturing 5D, which is 4D plus time domain, light field videos. They can only capture still light field images or are excessively expensive for normal users to capture the light field video. So our goal is simple. The goal is to synthesize multi-view video from a monocular video, which is commonly available for normal users. To tackle this, we propose a novel framework for 5D light field video synthesis by extending our previous work for 4D light field image synthesis. Our key contribution is first, we present an end-to-end network for synthesizing 5D light field video. Second, we present a new photorealistic synthetic dataset. Last, our network shows us the capability of synthesizing light field video for the real scenes. Deep learning-based methods require a large-size dataset to train the network. There are many kinds of open light field datasets. However, those datasets are consisting of still light field images and no video training dataset for light field video processing is available in the public domain. To overcome this limitation, we use a graphics-generated photorealistic video simulated in a virtual environment. We use Unreal CV to collect the synthetic light field video consisting of 9 by 9 sub-aperture images. Since we are using synthetic light field data, it is able to overcome the limitations of previous light field images such as low spatial angular resolution and small baseline. The proposed light field video synthesis framework consists of three sub-networks, namely feature extraction, 5D light field synthesis, and temporal consistency refinement. The appearance flow decoder estimates appearance flow using an encoded feature from the feature encoder to synthesize novel angular views. The occlusion network uses the variance mask from the initial light field video frame to refine the output. Meanwhile, the optical flow decoder estimates optical flow to give temporal consistency to synthesize light field video. The appearance flow represents 3D coordinate vectors specifying where pixels are mapped in the reconstruct novel views. Using estimated appearance flow, we synthesize the initial light field video frame by warping shifted input images and estimated appearance flow for each angular coordinate. To train the appearance flow network, we use the light field mean and variance losses which are proposed in our previous work. However, the synthesized light field video frame from appearance flow has a limitation such as poor quality on image boundary and occluded regions. To overcome this limitation, we formed a 9 by 9 variance mask using the initial synthesized light field video's variance image. The variance image of the light field represents a difference between each sub-aperture image, which is the occluded region of the scene. The network focused on hallucinating and synthesizing unseen pixels specifically in the occluded, edged, and boundary regions. Unlike 2D images, the light field image has an angular dimension in addition to the spatial dimension. To handle both dimensions simultaneously, like the previous method, the occlusion network is constructed with 3D convolution layers instead of 2D convolution layers. The occlusion network has a 3D encoder-decoder structure with an initial light field video frame and variance mask as inputs. To preserve the information of the angular dimension, the occlusion network maintains the size of the angular dimension while reducing and increasing the spatial resolution through encoder and decoder. Without this occlusion network, the output has noticeable artifacts near the occlusion and image boundary. To evaluate our methods qualitatively, we used the Kitty dataset and compared it with the previous state-of-the-art light field synthesis methods from a single image. We can see the proposed method synthesized more proper light field video than the previous methods. Including our previous work, previous methods failed to estimate correct geometry information of the scene, which leads to angularly inconsistent light field video. Previous methods failed to synthesize light field video in the smooth regions and shadows. The previous methods see the shadows as objects in the scene. Note that even if it is trained with a synthetic dataset, our method synthesizes more proper light field video in a real dataset. Additionally, we use Wang's dataset with a general scene to see our network's robustness. Even if we train the network with a synthetic driving scene dataset, it can generate more proper light field video than others. We evaluate our method with the state-of-the-art method for single image light field synthesis because no prior work was conducted on light field video synthesis. Since no light field video benchmark set is available, we use the synthetic light field video dataset for the quantitative evaluation. Test sets consist of 162 frames that are unused in the training. To evaluate our methods quantitatively, we use PSNR and SSIM. For the synthetic data number 1, which is challenging since it contains specular reflection and many high-frequency components, our method outperforms existing state-of-the-art method in terms of PSNR and SSIM. Also, for synthetic data number 2, our methods outperform state-of-the-art methods. So, in this work, we propose the method for synthesizing 5D light field video using a synthetic dataset. We also showed that the network can be extended effectively for the real scenes. Future work would include the generalization of the proposed method. Thank you for listening, and if you have any questions, please visit our course session.